All right, let's dive right into this explainer. Today, we're taking a pretty fascinating journey through the complete fuel system of the Bombardier Q400, and we're strictly following the ATA-28 system manual to do it. If you've ever found yourself wondering exactly how this aircraft stores, monitors, and manages its lifeblood, literally from the moment it's pumped on the tarmac to the split second it enters the engines, well, you're in the exact right place. We're going to break down the engineering logic step by step.
So, here's our flight plan for today. We'll kick things off with fuel storage and bays, move into system controls and displays, then engine feed and transfer. After that, we'll look at the refuel-defuel panel, and finally wrap up with the automatic refueling sequence. Let's get to it.
Starting off with Section 1, Fuel Storage and Bays, which is really where the whole journey begins.
Now, the very first thing to wrap your head around here is the sheer scale. Just look at this number, 5,318 kilograms, which is right around 11,724 pounds. That is the total usable fuel packed into these two wing tanks. I mean, that's a massive amount of weight and potential energy. Managing it safely requires some seriously brilliant internal architecture.
When we look at the internal anatomy, each wing tank is basically divided into three highly specialized sections. First up, you have the main tank. This extends from the surge bay to the fuselage and acts as your primary fuel containment. But check out the collector bay, located at the inboard and aft part of the wing. This is your continuous engine supply point. Through this really clever system of scavenge ejector pumps and gravity-fed flapper check valves, the system ensures this collector bay stays completely full. What that means for us is that the engines never run dry, regardless of the aircraft's attitude, whether it's pitching up or rolling. And finally, out on the edge, we have the surge bay. This is located outboard and is strictly used for main tank venting and recovering any fuel that might happen to spill over during flight.
Moving right along to Section 2, System Controls and Displays. Let's talk about how we actually monitor this journey.
What's really cool here is the straightforward, color-coded logic built right into the screens to keep the flight safe and balanced. Under normal operating conditions, your fuel quantity and temperature readouts are just simple white digits. But you know, the system is always watching. After the fuel passes through the fuel oil heat exchanger, the inlet temperature is constantly monitored. If that temp drops below 0 degrees Celsius, bam, those digits turn yellow. If the temperature spikes past 71 degrees Celsius, they turn red. And honestly, the manual strictly prohibits continuous operation at those extreme temperatures. The digits will also turn yellow, along with a flashing message if the system detects a lateral imbalance between the two wings.
So that begs a vital operational question about lateral stability. What actually happens if a fuel imbalance grows greater than 272 kilograms, that's 600 pounds, while a warning is triggered? When that happens, the analog quantity dials on the multifunction display actually change to solid yellow. So how does the crew fix it? That question perfectly transitions us into our next phase, moving the fuel.
That brings us to Section 3, Engine Feed and Transfer, where we balance the load. Now, here is a hard, absolutely crucial system limitation. You've got to understand that the Q400 only allows for tank-to-tank transfer. There's absolutely no engine cross-feed capability. None. You literally cannot take fuel from the left tank and feed it directly into the right engine. You can only move fuel from the left tank to the right tank, and then you have to let the right tank feed the right engine.
So how does the automated safety net of that transfer process work? Well, when the crew toggles the fuel transfer switch to 2-tank 1 or 2-tank 2, the system completely takes over. The auxiliary pump in the donor tank automatically fires up to push fuel across to the receiver tank. And the best part, you don't have to worry about accidentally overflowing the receiving tank. The transfer just continues until the crew deselects it or until a high-level sensor in the receiving wing detects an overfill condition, which instantly halts the process. And all the while, those scavenge ejector pumps we talked about are working continuously in the background to ensure the collector bays remain topped off.
Next up, Section 4, the Refuel and Defuel panel. Let's look at replenishing on the ground.
Down on the tarmac, ground crews have a really critical choice to make when operating this panel using a 5-position rotary selector switch. If they choose pre-select refuel, they're essentially setting a digital target on the indicator. The aircraft will hit that exact quantity and the high-level control unit will just shut it off automatically. Super easy. But if they choose standard refuel, it becomes a manual process. Fuel will just keep flowing until the crew physically switches it to the close or off position, or until the physical high-level sensors detect a completely full tank. And these numbers, they matter immensely out on the tarmac to ensure structural integrity and proper valve functioning.
The system demands a minimum operating pressure of 20 psi just to work. The absolute maximum refueling pressure is 50 psi, which translates to a max flow rate of about 125 gallons per minute. And this is key. DC power is strictly required for this panel to operate at all. If you somehow lose DC power during refueling, the entire operation instantly stops dead in its tracks.
Which leads us to our final section, Section 5, the automatic refueling sequence, step by step, following the strict constraints of the manual. Following the exact strict protocol for the Q400, let's walk through this 6-step sequence together. Step 1. For the visual, picture the Bombardier Q400 parked on the tarmac, and we zoom right in on the powered refuel-defuel indicator panel located on the rear underside of the number 2 nacelle. The explanation here is that when the panel is powered on, the pre-select quantity automatically defaults to your current total fuel quantity. And your memory aid? Power equals present. Turn it on, and it shows exactly what you already have. Step 2. For the visual, we have a clear shot of the panel focusing on the spring-loaded increment-decrement switch being toggled to enter a new pre-select value. The explanation is that you use the switch to set the desired amount of fuel for the operation, locking in your new target. Your memory aid for this is click to pick. Click the switch to pick your new fuel target. Step 3. Visually, imagine a countdown of 4 seconds next to the shutoff valves, which then physically open in the schematic. The explanation is that exactly 4 seconds after the switch is stable at the neutral position, the shutoff valves open and the automatic refuel function starts. The memory aid here? For to pour. Wait 4 seconds of no touching for the fuel to start pouring. Step 4. For the visual, you see the main wing tank cross-section filling up with fuel, side by side with the digital numbers on the panel continuously increasing. The explanation is simply that while valves are open and fueling is in progress, the tank fuel qualities on the indicator are constantly updated. Your memory aid, watch it rise. As the physical tank fills, the digital numbers go uphill. Step 5. Visually, the actual fuel quantity exactly matches the pre-select quantity on the panel, triggering a graphic of the shutoff valves immediately closing. The explanation here is that once the total fuel reaches that pre-selected amount, the high-level control unit automatically closes the valves, stopping the flow. The memory aid, match to catch. When the actual numbers match the target, the valves catch and close. And finally, step 6. The visual is a definitive green checkmark graphic over the fully fueled wing tank and closed panel door. The explanation is that the pre-select refuel operation is officially completed, and the aircraft has automatically received the exact requested fuel load. Your memory aid to wrap it up? Done and won. The fuel is secured and the sequence is complete. To wrap up this explainer, we've got to consider the ultimate worst-case scenario on the tarmac. Imagine this. What if you are pressure fueling at 125 gallons a minute, and both the automatic high-level control unit and the backup physical high-level sensors just fail simultaneously? Does the wing burst from the 50 psi of pressure?
The answer is just brilliantly simple. The fuel safely flows through a refuel vent valve directly into that outboard surge bay we talked about in the very beginning. Once the fuel in that surge bay reaches the height of the integral standpipes, it simply spills completely overboard onto the tarmac through the NACA vents located on the bottom of the wings. This final failsafe leaves us with a profound appreciation for aviation engineering. I mean, even when digital automation and redundant mechanical sensors completely fail, simple gravity and physics step in to protect the wing's structural integrity, ensuring the aircraft lives to fly another day. It really makes you wonder, if a multi-million-dollar aircraft ultimately relies on simple gravity as its final safety net, what other incredibly complex systems in our modern world secretly depend on basic physics just to keep us safe?